The B-52 is disintegrating, and Major Walter Tulloch has already lost. Not the fight to save his crew. 5 men will survive the incident. He's lost something else. 2 hydrogen bombs, each 260 times more powerful than Hiroshima, tumbling through darkness toward a tobacco field outside Goldsboro, North Carolina. The arming sequence has already begun. What happens next depends on a mechanism so simple, so mundane, that it would be almost funny if millions of people weren't potentially in the path of lethal fallout that could reach as far as Washington and New York. 4 safety mechanisms stand between a farming community and a thermonuclear detonation on American soil. As rescue teams race toward the crash site in the January cold, they don't yet know what they're looking for in the wreckage. They definitely don't know what's still missing. Part of one bomb was never recovered. It remains buried in the Carolina soil to this day. The other landed largely intact, its parachute deployed, resting in the soft earth. When the Air Force finally examines the weapon and cracks open the arming panel, they discover something that will remain classified for 52 years. A single switch position that shouldn't be possible. Earlier that night, while cruising at high altitude, Major Walter Tulloch commanded the B-52G on Operation Chrome Dome, carrying 2 Mark 39 hydrogen bombs in the bomb bay, each with a yield of 3.8 megatons. Chrome Dome missions keep nuclear-armed bombers airborne around the clock to ensure second strike capability against Soviet attack. Tulloch and his crew have flown this route a dozen times, refueling mid-air on patrol routes designed to intercept Soviet forces approaching North America. The mission is routine. The bombs hang on steel shackles with electrical umbilicals feeding arming signals and mechanical lanyards bundled to parachute packs rated for controlled jettison over water. Shortly after midnight, the bomber met with a tanker to begin refueling. The boom operator reports normal flow as the tanker pumps JP-4 into the B-52's wing tanks to extend the patrol another 6 hours. This is a thermonuclear weapon, the Mark 39. Inside, a plutonium fission primary that triggers fusion in a lithium deuteride secondary, the part that levels a city. The yield? Multiplied by a factor of hundreds. Between you and detonation, 6 safety locks. 6 steps that must close in sequence: a barometric switch, a time delay relay, an environmental sensor, a high-voltage thermal battery, a capacitor charge for the detonator, and finally, a low-voltage arm-safe switch. Every single one requires intentional pilot action from the cockpit panel. The design assumes controlled release, combat conditions, not uncontrolled separation during structural failure. Without pilot input, the weapon should remain safe. That assumption is about to be tested in a way no one at Sandia Labs ever anticipated. The bomber circling overhead isn't on a training run. Chrome Dome is a standing posture, a calculated gamble that keeps part of America's nuclear arsenal in the air, always moving, impossible for the Soviets to destroy in a first strike. Bombers fly predetermined tracks over the Atlantic, the Arctic, the Mediterranean. 24 hours aloft, multiple mid-air refuelings, crews so exhausted they're flying on procedure and muscle memory alone. And here's the part that should terrify you. If Washington gets vaporized in a surprise attack, these airborne crews have pre-delegated release authority. They can launch without asking permission from anyone, under specific conditions. At its peak, dozens of missions like Tulloch's were in the air simultaneously, each one carrying live thermonuclear weapons over friendly and neutral territory. The system trades peacetime risk for wartime survivability. The procedure manual covers a lot of scenarios: engine failure, navigation errors, communication loss. It assumes the aircraft will remain structurally sound. It does not address catastrophic airframe failure while carrying a live nuclear payload. The bombs remain on safe configuration with all arming steps locked out, but the mechanical lanyards connecting the weapons to their parachute packs have no breakaway threshold. Any separation from the aircraft will yank the lanyards and deploy the chutes automatically. The parachute system was designed primarily for retarded delivery, allowing the bomber to escape the blast radius during low-altitude attacks. According to some accounts, this configuration also facilitated deliberate jettison over open ocean, where the parachute would slow descent and allow time for the weapon to sink before deep water recovery. But it was not designed for unintended separation over land. The lanyard is a simple steel cable with a spring-loaded pin. Once the weapon drops free, physics takes over. The parachute deploys, the weapon stabilizes in vertical descent, and the barometric switch begins counting down altitude. There is no abort mechanism, no external override. The bomb is now following its programmed sequence. B-52G design relocates external fuel tanks outboard on the wing to increase range, but the added bending moment accelerates fatigue cracks in the wing root attach fittings after 3,000 flight hours. Telek's aircraft has logged roughly 3,600 hours. Maintenance crews documented hairline cracks in the right wing spar during the last depot inspection, but cleared the airframe for continued operations under reduced load limits. The Air Force accepts this as normal wear. The wing is still within structural margins for routine flight, but those margins assume steady-state cruise. They do not account for the dynamic loads imposed by mid-air refueling, where fuel mass shifts aft in the wing tanks and raises local stress on the already compromised spar beyond the original design envelope. Off the coast of the Carolinas, the tanker boom locks in. JP4 fuel begins flooding the wing tanks at 600 gallons per minute. That's not just fuel, that's weight, rushing aft through the tanks, roughly 6.5 pounds per gallon, shifting the wing's center of gravity outboard with every second. Thousands of gallons of fuel per wing. The bending moment at the root climbs. The aircraft was designed for this, but the design assumes an intact spar. It doesn't have one. The hairline cracks, invisible, buried deep in the aluminum, act as stress concentrators. As the fuel mass shifts aft, the wing flexes. The cracks amplify the vibration. Each refueling cycle feeds the fracture. Telek's crew feels nothing. The instruments read normal. Flow normal, pressure normal, wing loading normal. But inside the spar, metal is tearing, one oscillation at a time. And there is no sensor that can detect it in real time. The wing is failing. The clock is ticking. And no one knows. There is no procedure to save the weapons during structural emergency. The checklist assumes controlled jettison over open ocean with pilot-commanded release, not catastrophic airframe failure. The cockpit arming panel has a master switch, but it controls only the final step in the sequence. The earlier steps, barometric, timer, environmental sensor, are fully autonomous once the weapon separates from the aircraft. The crew cannot disable them in flight. The bombs are designed to survive jettison and remain safe on impact, but that design assumes the parachute will not deploy. If the parachute deploys, the weapon interprets the event as an intentional release and begins arming automatically. The procedure manual does not address this scenario because the scenario was never supposed to happen. The bombs are supposed to stay attached to a flyable aircraft. The wing is holding, but only just. Each refueling cycle has pushed the crack a fraction of a millimeter deeper into the spar. The aluminum alloy is strong, but fatigue is cumulative. The wing had endured hundreds of flight hours and cycles since its delivery in the late 1950s. Each cycle consumes a small amount of the material's remaining fracture toughness. The inspection manual specifies crack growth limits, but those limits are based on steady-state flight, not the dynamic loading of mid-air refueling with a compromised spar. The wing is now operating outside the tested envelope. The crew cannot see the internal damage from the cockpit. The warning lights are dark. The aircraft is maneuvering for refueling when the tanker pilot spots something wrong. A fuel leak streaming from the wing. The alarm is raised. The mission is aborted. Shortly after midnight, the right wing spar fails catastrophically at the fuselage junction. The wing twists upward, rupturing fuel cells and severing hydraulic lines that control the rudder and ailerons. Tulloch loses elevator authority as the aircraft enters a flat spin. He orders bailout. The navigator, bombardier, and tail gunner eject within 30 seconds, while the aircraft descends through 8,000 feet. The airframe is disintegrating. Pieces of the wing separate and tumble through the darkness. The fuselage rolls inverted. The bomb bay doors, no longer supported by intact airframe structure, tear away from their hinges. Both Mark 39 weapons fall free. Their lanyards yank the parachute packs. One 28-foot diameter canopy deploys, stabilizing its bomb in vertical descent. The other weapon tumbles freely through the darkness. The crew is fighting to survive. The bombs are following their programming. The parachute snaps open. First arming step, complete. At a preset altitude, believed to be around 10,000 feet based on the aircraft's flight path, a barometric switch clicks closed. 28 volts surge through the arming bus. The second step unlocks, a time delay relay set for 15 seconds after separation. Inside the casing, a simple aneroid sensor, the same type used in altimeters. As the bomb falls, air pressure builds. A sealed bellows compresses. At the preset altitude, it collapses just enough. Electrical contact closes. The circuit is live. The bomb has no way to distinguish between an intentional release over a Soviet target and an uncontrolled fall over North Carolina. It is doing exactly what it was designed to do. The timer starts counting. 15 seconds until the next step closes. The bomb descends at roughly 20 feet per second under the parachute. Below, the crew is scattered across 3 miles of darkness, some already on the ground, others still falling. No one is watching the bombs. The crew ejects at high altitude as ordered, though the disintegrating aircraft continues its descent. 5 of the 8 crew members survive the bailout, while 3 are killed. The tail gunner's ejection seat fires successfully, but he does not survive the landing. 2 crew members, the radar navigator and the electronic warfare instructor, remain in the fuselage and are killed when the wreckage hits the ground. The survivors are scattered across miles of rural farmland and forest. Some suffer serious injuries from the high-altitude ejection. They have no radio contact with each other and no way to coordinate. They do not know where the bombs are. They do not know if the bombs are intact. They do not know that one weapon is already 5 steps into its arming sequence. The aircraft impacts a tobacco field and disintegrates, scattering wreckage across 3 miles. The fuselage breaks into 4 major sections. The wings separate completely. Fuel ignites on impact, creating a fireball visible for 20 miles. Local residents call the sheriff's office reporting a plane crash. The first responders arrive within 30 minutes, but have no specialized training for nuclear accident response. They see wreckage, fire, and bodies. They do not see the bombs. One weapon landed a quarter-mile east of the main impact site, parachute fully deployed, nose cone buried in soft ground. The other struck harder, driving through the surface and into waterlogged clay. Both are now beyond visual range of the crash site, lying in darkness while their internal systems continue to execute the arming sequence. The responders are searching for survivors. They are not searching for live nuclear weapons. The Mark 39 arming sequence requires 6 independent closures in series. Step 1. Barometric switch at 14,000 feet. Step 2. Time delay relay 15 seconds post-separation. Step 3. Environmental sensing device confirming freefall acceleration. Step 4. High voltage thermal battery activation. Step 5. X-unit capacitor charge for detonator bridge wire. Step 6. Low voltage arm-safe switch toggled by cockpit panel. Each step must close in order. The design assumes controlled release under combat conditions with the pilot actively commanding detonation. The sequence is intended to prevent accidental detonation during routine handling, transport, or minor accidents. It is not designed to handle catastrophic airframe failure with parachute deployment during an uncontrolled descent over friendly territory. The designers at Sandia Labs never tested that scenario because it was never supposed to happen. Bomb number 1 lands in a field with parachute fully deployed. Post-recovery analysis shows steps 1 through 5 completed successfully. The barometric switch, which was found with its contacts closed, was intended to sense the drop in altitude after release. The timer successfully completed its full sequence. The environmental sensors, designed to detect the physical conditions of release, correctly registered the separation from the aircraft. The thermal battery ignited, delivering high-voltage current to the firing circuit. The X-unit capacitor charged to 3,000 volts, ready to drive current through the detonator bridge wire. Each step functioned exactly as designed. The weapon reached a configuration indistinguishable from a live combat release. Only step 6 remained, the arms safe switch. That switch was still in the safe position, interrupting the firing circuit between the charge capacitor and the detonator. In a configuration that indicated nearly all arming steps were complete, that single switch was the only thing standing between a farming community and a 3.8 megaton surface burst. Step 6, the arm safe switch, is a simple rotary selector with a mechanical detent. In safe position, it interrupts the firing circuit between the X-unit and the detonator bridge wire, which requires 50 amps for 50 microseconds to initiate the high explosive lens. The switch has no backup, no interlock, and no redundancy. It is a single mechanical component in a circuit carrying the final firing command. If vibration, impact, or electrical transient had rotated it to arm position during descent, the charged X-unit would have fired the bridge wire immediately. The bridge wire ignites the high explosive lens. The lens implodes the fissile primary. The primary releases neutrons and X-rays that compress and ignite the lithium deuteride secondary. The fusion reaction runs to completion in microseconds. The result is a 3.8 megaton surface burst. A 3.8 megaton surface burst yields a fireball 3 miles wide. Peak overpressure of 20 pounds per square inch extends out to 2.5 miles, sufficient to collapse reinforced concrete structures and kill anyone not in a hardened shelter. Third-degree burns occur at 8 miles, well beyond the distance anyone could cover after seeing the flash. Fallout deposition begins within minutes. Prevailing winds carry radioactive debris northeast across Virginia and Maryland. Within 12 hours, depending on wind speed, lethal radiation doses reach the outskirts of Washington, D.C. and Baltimore. Based on 1961 population density, the immediate death toll is estimated between 28,000 and 30,000, though modern assessments suggest the figure could exceed 60,000 today. Long-term cancer deaths from fallout exposure could exceed 100,000. The weapon that nearly detonated fell approximately 12 miles from Goldsboro, a town of nearly 29,000 people. At that distance, thermal effects would have caused catastrophic burns across the entire town. Survival would have been extremely unlikely. The switch remained in safe position, not because of any engineered safeguard, but because of luck. The weapon experienced violent acceleration during separation, parachute deployment, and ground impact. Each event subjected the switch to shock loads far exceeding its design environment. The mechanical detent holding the switch in safe position is a spring-loaded ball bearing seated in a notch on the rotary shaft. Laboratory tests conducted after the accident show that shocks above 15 Gs can overcome the detent force and allow the switch to rotate freely. The weapon experienced peak deceleration near 20 Gs when the parachute opened. The switch could have rotated. It could have closed. It did not. Post-recovery inspection found the detent intact, the switch still seated in safe position. There is no engineering principle that explains why. The outcome was not determined by design margin or procedural safeguard. It was determined by chance. Bomb number 2's parachute fails to deploy fully. The weapon impacts soft ground at terminal velocity, driving the secondary stage, containing the lithium deuteride fuel and uranium tamper, through the casing and into saturated clay below the water table. The primary stage, with its uranium-based fission core and high explosive lens, is recovered from a depth of roughly 20 feet. The secondary continues downward, propelled by momentum and the hydrostatic pressure of the waterlogged soil. Instruments on the surface detect radiation from the primary, but no signal from the secondary below 50 feet. The weapon is now in two pieces, separated by dozens of feet of unstable, water-saturated clay. The high explosive lens remains shock-sensitive. Any drilling, vibration, or pressure shift risks detonation of the chemical explosive, which would not produce a nuclear yield but could potentially disperse radioactive material into the local environment. Lieutenant Jack ReVelle's EOD team arrives 18 hours post-crash with no specialized equipment rated for live nuclear ordnance extraction. They dig by hand, using shovels and a water jet probe to map the cavity. The water jet cuts through clay without generating sparks or vibration that could trigger the high explosive lens. They locate the primary stage at 15 feet and begin excavation around the weapon's core. Below, there is no signal from the secondary. The water table is high, the clay is unstable, and every shovelful risks shifting the soil and collapsing the cavity onto the primary. ReVelle's team works in shifts, round the clock, under floodlights. The city of Goldsboro lies approximately 12 miles away. If the high explosives had detonated, radioactive material would have contaminated the groundwater and surrounding region. They dig carefully, measuring radiation levels every 6 inches, but the secondary remains out of reach. The high explosive lens surrounding the plutonium pit is shock sensitive. Any unstable drilling, vibration, or hydrostatic pressure shift risks detonation of the chemical explosive. The explosive is Composition B, a mixture of RDX and TNT, designed to implode the plutonium core symmetrically. If it detonates asymmetrically, triggered by mechanical shock instead of precisely timed detonators, it will scatter plutonium fragments across the site and into the groundwater. The clay is waterlogged, and the water table feeds the Neuse River aquifer, which supplies drinking water to Goldsboro and downstream communities. A single gram of plutonium-239, if ingested or inhaled as particulate, delivers a lethal dose. The weapon's core is estimated to have contained several kilograms of fissile material. The standard plutonium pit in similar designs held approximately 6 kilograms. ReVelle's team is trying to extract the primary without disturbing the explosive. They have no equipment designed for this task. They are improvising, one careful shovelful at a time. After several months of effort, reaching a depth of roughly 42 feet, the Air Force halts excavation. The primary stage has been recovered, disarmed, and transported to Kirtland Air Force Base for analysis. The secondary remains buried, somewhere below 50 feet in waterlogged clay. Additional drilling risks rupturing the components, potentially releasing uranium and lithium deuteride into the groundwater. The Air Force decides the risk of continued excavation exceeds the risk of leaving the component in place. They purchase a permanent easement over the site to prevent deep excavation. Soil and water samples are collected and analyzed for contamination. It is the first time the U.S. military has abandoned a live thermonuclear component on domestic soil. The easement remains in effect. The secondary is still there, beneath what is now a soybean field, under Air Force custody, but beyond physical reach. ReVelle testifies about what he found in that field. Bomb number 1's arming panel. He photographs it and sends it to Sandia Labs. The weapon designers open the analysis, expecting confirmation of their fail-safe system. Instead, they're stunned. 5 indicators glow green. 5 autonomous steps completed during freefall. The barometric switch, the timer, the environmental sensor, the thermal battery, the X-unit capacitor, all functioned exactly as designed. But here's what stops them cold. According to ReVelle's account, one switch position showed the weapon had moved toward an armed state. The cockpit panel was in safe position when the aircraft disintegrated, There was no pilot action to trigger the arming sequence. No human command was ever given. The weapon did not malfunction. It worked perfectly. Every component performed exactly as intended, under conditions they were never intended to experience. The Mark 39 was supposed to require active pilot commands to arm. That assumption was the foundation of the entire system. The problem was not hardware failure. The problem was design philosophy. The arming sequence assumed the weapon would remain attached to a flyable aircraft. That assumption was wrong. No detonation occurs. Bomb number 1 is disarmed in the field and transported to Kirtland Air Force Base for forensic teardown. Bomb number 2's secondary stage remains buried under a fenced monitoring station that the Air Force inspects periodically for radiation leakage. The crew survivors are debriefed. Tulloch survives his injuries, though his subsequent flight status remains unclear in public records. The 3 fatalities are buried with military honors. The crash site wreckage is cleared, and the tobacco field is returned to agricultural use. Local residents are not informed of the weapon's arming status or the proximity to detonation. The Air Force issues a press release stating that 2 unarmed nuclear weapons were recovered following an aircraft accident with no risk to public safety. That statement is technically accurate. The weapons were not armed by pilot action. It does not mention that 5 arming steps completed autonomously. Sandia Labs convenes an immediate review of all gravity bombs in the stockpile and finds that 11 out of 14 weapon types rely on single-point mechanical switches with no redundancy. The ArmSafe switch is not unique to the Mark 39. Similar designs appear in the B-43, the B-57, and the W-44. Each weapon assumes that separation from the aircraft will occur under controlled conditions with pilot oversight. None of them have mechanical interlocks to prevent autonomous arming during uncontrolled descent. The review panel concludes that the Goldsboro incident exposed a systemic design flaw. The weapons are not unsafe under normal handling. They are unsafe under abnormal conditions that were never tested because they were assumed to be impossible. Secretary of Defense Robert McNamara orders a 6-month retrofit program to add electromechanical interlocks and coded permissive action links to all frontline weapons. Here's what the Pentagon realized after Goldsboro. They'd been flying nuclear bombs with a design flaw that could kill millions. And it wasn't just one bomb, it was thousands. The fix was called Permissive Action Links, PALs, coded electromechanical locks that require a multi-digit code entered by the crew before the weapon can arm. The code is transmitted from higher authority and changes with each mission. Without the correct code, the arming circuit remains open, regardless of switch position or environmental inputs. It's a last line of defense between a mechanical failure and a detonation. The earliest PAL systems used simple combination locks with 4-digit codes. Later versions incorporated tamper-resistant encryption and physical self-destruct mechanisms if unauthorized entry was attempted. The retrofit program began in 1962, initially prioritizing weapons stationed abroad, then gradually expanding to cover the domestic arsenal. A multi-year scramble to lock down thousands of bombs that had been vulnerable since day one. The Mark 39 was withdrawn from service in 1966. Its replacement, the B-53, represented a new generation of thermonuclear weapons, though it would take years before comprehensive safety upgrades, including PAL systems and redundant interlocks, became standard across the entire stockpile. The single-point mechanical switch was eventually retired. The new designs required at least 2 independent failures before a weapon could arm unintentionally. The margin of safety was no longer determined by a single component. The question is, how many other bombs came that close before they fixed it? The Air Force quietly ends Operation Chrome Dome in 1968 after 4 additional accidents involving nuclear-armed aircraft. The strategic calculus shifts. Ground alert posture keeps bombers fueled and armed on runways, ready to launch within minutes, but not exposed to mid-air refueling failures or structural fatigue over long patrols. Submarine-based deterrence, using Polaris and later Trident missiles on SSBNs, provides continuous at-sea presence without the airborne vulnerability of Chrome Dome. The bombers remain part of the triad, but they no longer fly routine nuclear patrols over populated areas. The policy change eliminates the scenario that led to Goldsboro, a live weapon in freefall over friendly territory with no pilot control. Chrome Dome was a calculated risk during the height of the Cold War. After Goldsboro and subsequent accidents, the calculation changed. The risk was no longer acceptable. The Goldsboro incident remains classified until 2013, when declassified documents reveal that the weapon came within a single switch of full-yield detonation. The documents include forensic reports from Sandia Labs, recovery photographs, and internal memos assessing the arming sequence. One memo, written in 1969 by weapon designer Parker F. Jones, summarizes the incident in a single sentence. One simple, low-voltage switch stood between the United States and a major catastrophe. The memo circulates within the nuclear weapons community, but is not released to the public for another 44 years. When the documents are finally declassified, they confirm what ReVelle and the EOD team knew in 1961. The weapon was one mechanical failure away from detonation. The arming sequence completed 5 of 6 steps without pilot action. The 6th step held not because of robust design, but because of chance. The site easement remains in effect. The unrecovered secondary stage lies beneath a soybean field, a permanent reminder that engineering margins and procedural safeguards are only as reliable as their weakest physical component. The Air Force conducts periodic monitoring of the site, measuring for radiation releases, though the exact frequency and specific isotopes tested are not part of the public record. No leakage has been detected. The secondary stage remains sealed deep beneath layers of waterlogged clay. Its physical condition is unknown, though it appears to be effectively contained by the surrounding environment. The field is privately owned, but subject to Air Force access rights. The farmer plants and harvests around the fenced monitoring station. Locals know the site as the place where a bomber went down in 1961. Most do not know that a thermonuclear weapon component is still buried there, deep within the earth, far beneath the topsoil and the seasonal crops above. Weapon did not detonate, but it is still there. The Goldsboro incident is not a story of malfunction. It is a story of design assumptions tested under conditions that were never anticipated. The Mark 39 worked exactly as designed. The problem was that the design assumed the weapon would remain under pilot control. When that assumption was violated by catastrophic airframe failure, 5 arming steps completed autonomously, and a single mechanical switch determined the outcome. Engineering margins exist to absorb uncertainty, but they cannot absorb scenarios that were never considered. The retrofit of PAL systems and redundant interlocks address the specific vulnerability exposed at Goldsboro, but the broader lesson remains. Safety is not a property of individual components. It is a property of the system, and the system is only as reliable as its weakest assumption. A Mark 39 bomb of the same type is now on display in a museum. The secondary stage is still in the ground, and the question remains: what other assumptions are we making?